Now, in the previous video, we showed that if I have a vector function like this, let's say I have a vector function r of t, so we have some scalar variable t, we can express this as rx of ti plus ry of tj plus rz of tk, right? So we have some vector function where each of these are my x, y, and z components of this vector, right? This vector function. And if I were to find the derivative of this with respect to t, all that I would have to do is find the derivatives of each of these individual components with respect to that variable t. So I would have d rx by dt I, d ry by dt j plus d rz by dtk. This will be the derivative of my vector function, right? But how do we know that in order to take the derivative of some vector function, I will actually have to find the derivatives of my x, y, and z components with respect to that variable? How do we know that this is how to find the derivative? Well, if I go back to the limit definition of a derivative of some function, let's say I have some function f, then according to the limit definition of the derivative, it is defined as the limit delta x approaches 0, where delta x is some change in x, f of x plus delta x minus f of x divided by delta x. So if I were to draw an arbitrary, the graph of some function like this, then let's say I have some point here, some point here, right? So what do we have in the numerator? In the numerator, this is just giving us the vertical distance between 2 points, right? And in the denominator, we just have the horizontal distance between 2 points. If I have a point P and some point Q, this is delta x, and this is f of x plus delta x minus f of x. And as this change in x gets closer and closer to 0, as it gets infinitesimally small, then my point Q gets closer and closer to P, and it gets so close that until at some point the difference between these 2 points becomes indistinguishable, right? And then according to the limit definition, the derivative will just be equal to the slope of this line at this particular point of my curve. So I will just get the tangent of the curve at this particular point, right? I will get the slope of the tangent line of the curve at this point. So applying this for a vector function, r of t, so if I find, let's say I'm now referring to the displacement or position vector of a particle, right? And t here is representing time, right? Then r prime of t is equal to the limit delta t approaches 0, r of t plus delta t minus r of t divided by delta t, right? So similar to how in the previous case we had the tangent to the curve at the point P, for a vector function, the derivative will be defined as the tangent vector of some space curve at a particular point, right? So I'll get a tangent vector to a space curve. So if I consider a three-dimensional coordinate system, this is my x, y, z axis. If I'm considering some space curve like this, right? What is a space curve? This is just a curve that is passing through three-dimensional space, right? That is a space curve. So if I have some point P, right, we have a particle that is passing through this curve at a specific point in time, let's say t, and at that time we have the particle at this point P, right? And we can represent the position of this particle using my position vector. We will have a position vector r of t, and after some time elapses, after some change in time, delta t, our position of the particle will be at some point here, let's say q, right? And this will have a position vector like this, r of t plus delta t, right? So after some change in time. So what we can do is we can just represent delta t, this change in time, with a vector from P to Q, right? So this is delta t. So if I find the derivative of a vector function, I will get a tangent vector to this space curve. So what happens when delta t approaches 0? What happens when delta t gets smaller and smaller and closer to 0, right? Then in that case, this point Q gets closer, and then we will have a line like this. And as it gets closer and closer, we start to have lines like this. And until Q is almost very close to this point P, we will just get a vector like this, right? And this will be my tangent vector to the space curve at this particular point, right? So when I take the derivative of a vector function, a of s, I will just get a tangent vector to the space curve, like I have here. Like this is just the tangent to this curve at point P. So now if I go back to the limit definition of the derivative of this vector function, I had r of t plus delta t minus r of t divided by delta t, and delta t is approaching 0. So what I can do is, since I have the difference of two vector functions in the numerator, what I can do is I can write this in terms of its components, right? I will have the limit delta t approaches 0. I will have rx of t plus delta t I plus ry of t plus delta t j plus rz t plus delta t k. So that is for this vector function here. Now considering r of t, I will have minus rx of t I plus ry of t j rz of t k divided by delta t, right? So what I can do is I can group my I components, j and k components together, right? So I can write this as the limit delta t approaches 0, rx of t plus delta t minus rx of t divided by delta t I plus ry of t plus delta t by delta t j, and then for k, so as you can see here, we have these three different terms, right? And we're finding the limit delta t approaches to 0 for each of these terms, right? So what does this look like? This should obviously be familiar with you. If I take the derivative of some function, this should resemble the derivative of some function like this, right? As you can see, this is exactly similar to what we have here, right? So very obviously you can see that what we end up having is just the derivative of my x component with respect to t I, and here this is just the derivative of my y component ry with respect to time, dry of dt j, and then for the third case, this is just the derivative of my z component with respect to t k, right? And this is equal to r prime of t, right? So now we have shown that if I have some vector, to find the derivative of that vector, I will just have to find the derivative of the individual components of that vector with respect to that variable that we're considering, right? So now we have shown how to find the derivative of any vector function.